Okay, so second section we're going to look at this week is 11.2, and it's on what's called series. Quick explanation is a series is when you add up all the numbers in a sequence. That's all. So we're going to look at ways to do that efficiently. Because if you've got a sequence with thousands and thousands of numbers, you don't have to know every number in the sequence to add them all up. There's a way to add them up without knowing what they are. So we got to look for patterns. Okay, more patterns today. So in the last section, we used this notation to denote a sequence. A sub n equals, and then we have a rule for it. This one happens to be a quadratic pattern. So probably one that would be a little harder to do by hand. So now, what we're going to look at is we're going to look at some sums. And I'm going to use the notation S sub n. What that means is S sub 1 would mean what you get when you add up the first one term in that sequence. S sub 2 would be what you get when you add up the first two terms. S sub 10, what you get when you add up the first 10. So, what it would be helpful to do is write out some of the terms in that sequence so we know what we're adding. All right, if I plug in 1 for n, okay, let's go like this. N, a sub n. What's my first term going to be in the sequence a sub n? One. Yep. Let's do the second term. My second term is going to be 9. Let's just write it out maybe up to the fourth term. That's enough. What's my third term? 25. And my fourth term? 49. Okay. So now let's find the sums. What would you get if you add up the first one term in those numbers? Just add up the first one terms. Yeah. Yeah. So if you want, you might see the pattern if I actually wrote it like this. This is really 1 squared, 3 squared, 5 squared, 7 squared, 9 squared. It's odd numbers squared. That's the pattern here. Okay? And I think if you write it like that, you see it a little easier. Right? So the first number is just 1 squared, or just 1. S sub 2 means to add up the first two terms in that sequence. What do you get if you add up the first two terms? 10. You get 1 squared plus 3 squared, which is 1 plus 9, or 10. Okay. What do you get if you add up the first three terms? How much? 35. Yep, you get 1 squared plus 3 squared plus 5 squared. That's 35. So the goal would be, all right, if we want to know what would you get if you add up the first 20 terms, well, you want to look at these numbers in red and try to find a pattern for the numbers in red, because these numbers represent sums. If you can find a pattern to the numbers in red, then you can predict what the sum of the first 10 terms or 50 terms or anything would be. And you don't have to go through and find each term. So the nth term, I can't really write what the answer is because I don't know how high n goes. It doesn't say that there's any limit on it. But if you wanted to add up the first n terms, it would be 1 squared plus 3 squared plus 5 squared plus 7 squared plus all the way up to the very last term, which would be 2n minus 1 squared. And you'd have to fill in whatever n is. Okay, so this dot 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 just means that there's an undetermined amount of terms in there. I don't know how many. But any questions on S1, S2, S3? Okay. And I'm going to write this in a second, but what these are called is partial sums. Okay, a partial sum of the first two terms. A partial sum of the first three. I know the first one sounds weird. It's a partial sum of the first one term. It's just really the first term. Okay, so each S sub n, I'm going to put this 2 pages at the same time, that we came up with is called a finite series. Finite means it has an end. Series means you're adding. 1 squared plus 3 squared. That's a finite series. It ends, and there's addition. 1 squared plus 3 squared plus 5 squared. There's an end to it, and you're adding things up that have an end. So finite because it has an end. Series because you added up a bunch of things to get the result. Okay, so when you see the word series, you want to think sum. Series, you're adding things up. So now, suppose I took these numbers here in red and I made a new sequence out of them. 1, comma, 10, comma, 35. What I just created right there, that is called a sequence of partial sums. It's a sequence because it's a list of numbers separated with commas. And each number in the sequence was obtained from adding up stuff. Okay, you added stuff together. Right, what did you add together? Well, for the first term, you added the first 1 terms in your sequence. To get the second term, you added the first 2 terms in your original sequence. To get S sub 3, you added up the first 3. If you wanted S sub 4, you would add up the first 4 terms. So it's a sequence where each number represents a sum. And that's what I'm trying to show you right there. S sub 4 would be A1 plus A2 plus A3 plus A4. So they'll give you a formula. So you're not gonna have to figure that part out usually in this section. What you are gonna have to figure out is a quick way of adding everything up. And that can be a little tricky. I doubt anybody sees a pattern here, 1, 10, 35. Even if I gave you more numbers, you'd still have a hard time figuring out the pattern of those numbers in red. Okay, so when the pattern gets really difficult, that's where the calculator can figure out the pattern for you. But I'm going to give you ones that either they're known patterns, so we're going to learn, like, if you see this, this is always how you do it. So there's like tricks to look for. Okay. So S sub 1 is called your first partial sum, S sub 2 second, third partial sum. This one is the nth partial sum. From the first term up to the nth term. So writing something like this gets kind of time consuming. If I wanted to write S sub 50, I don't want to write A1 plus A2 plus A3 all the way to A50. It's going to take a while. So I'm going to show you a notation that allows you to express the same idea with a lot less writing. Now, this notation doesn't speed anything up. For now, if you guys wanted to know the first 50 terms in that sequence we just did, what they add up to, the only way you know how to do it right now is to write all 50 down and then add them up. Okay. We're going to learn a faster way. But for now, I'm at least going to show you a faster way to write the concept, not to do it though. Okay. And it's called sigma notation. All right. So if you wanted to add up a bunch of numbers from the first term to the nth term in a sequence I'm calling A, this is how you write it. First of all, you put that capital Greek letter sigma. This basically tells you where you're starting. This tells you where you're stopping. This is the formula you're using to generate the numbers that you're going to add. Okay, so that you got to have a formula here. Okay, and the k, see if I write it later on, but the k is called the index. Did I write that? Yeah. So the way you pronounce this is you would say the sum from k equals 1 to n of the numbers in this sequence. Okay, and you'd have a formula for that sequence. Okay, so the index is it's just like a counter. It's like a variable that just keeps track of where you are. And this number always goes up by 1 each time. Okay, so you start at 1, then you go to 2, then 3, then 4, then 5, till you get to whatever the number is up here. Okay, the top will be a number. So, for example, let's look at this one. Let's take and we're going to expand this out. So that's called sigma notation. And this represents the sum of the first 5 terms in the sequence 2k plus 3. So if somebody was looking at that and they didn't know what it meant, you could write it out by plugging in each number from 1 to 5 for k and then adding them all up. So let's start with 1. If you plug in 1 for k, what's your first number? 5. What if you plug in 2 for k?
7.
It's 7. And 3? Yeah, 9. 4? 11. And Joe, what if I plug in 5 and that's the last one I'm going to stop at? 13. Why did I stop with 5? Because there's a 5 there. So it says plug in every number from 1 to 5, counting by 1s, going up by 1s, into that formula. So as I said, it gives me a nice short way to write it, but to actually do this all out, I still have to add all that stuff up if I really want to do it out. Okay, I'm not going to add it all up, but you could. Okay, so on the left, what I have is called sigma notation. On the right, this is expanded notation. You've actually written the whole thing out. Okay, any questions on that notation? All right. So actually, I already told you this. When you use that symbol, that sigma notation, when you expand it out like we did on the other page, that's called expanded notation. So if you just write, I mean, you really could just put an arrow here and write sigma notation, expanded notation. Just write it right underneath. So sigma notation, expanded notation. Okay, so it's nice to have a short way of writing something when you want to add up a bunch of terms, but it would also be even nicer to have a faster way of just doing it, rather than doing it out, thinking of it expandedly. Okay. It's okay for 5 terms, 500 terms? No. You got to come up with a faster way. Okay, let's expand this one. All right, so this has an n here. So when it has an n, all you have to do is kind of show me the pattern. Show me what's happening, maybe the first 3 or 4 terms, and then ... and then we'll plug in n as the last number. Okay, but what I want to try to understand here is this is not infinity. N is a specific number. It stops somewhere. Where does it stop? I don't know. It stops at n. But the point is, it stops. Okay. So, let's expand this out. Kathleen, if I plug in 1 for k, what do I get just in the parentheses? 5. I'm just going to leave it like this. 5 squared. I mean, you can write 25 if you want. That's fine. But if you leave it as 5 squared, you'll see a pattern. Robin, what if I plug in 2 for k?
7 squared.
Yep, 7 squared. And Nate, what if I plug in 3 for k?
9 squared.
9 squared. So basically the pattern here is it's odd numbers squared. So plus dot, dot, dot. Okay, I can see the pattern. What's the last number I would plug in for k? The highest one. N. So the last term is 2n plus 3 squared. So when you have to expand something that goes to n, just do it like that. Show me the first 3 or 4. The 3 is okay. Then just put plus dot, 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 and then show me the last term. And if you want to write 25, 49, 81, you can do those out, but if you don't, that's fine too. Okay. Any questions on expanding that sum? Now, when it goes to n, you can't get a numerical answer because we don't know what n is. All right. So now we're going to look at some properties of summations. I'm going to show you some properties that would basically let you do a problem like this. You have 2 separate summations. I'm going to show you how you can combine them into one. And it's pretty much what you would think. It's almost like combining like terms. You'll notice my sigmas get worse as I go on. If I'm going to draw it properly every time, it should look like that. But when I start drawing it quick, I don't know, they get bad. So, all right. So A sub n and B sub n just represent 2 different sequences. So the first rule is basically saying that if you want to add 2 different sequences together, you can do it 2 different ways. You can add the sequences together first, and then add that result. Or you can add up everything in the first sequence together, write that number down. You can add up everything in the second sequence, write that number down, and then add those 2 numbers up. I'll show you with some simple numbers, but it's going to come out exactly the same each way. Let's let A sub k be the sequence 1, 3, 5. Okay, short, simple sequence. Let's let B sub k be the sequence 2, 4, 6. So let's do what it says on the left. Add the sequences together. That's in parentheses, so let's do it first. Okay. When you add sequences together, you do it just like you would think. Add the first term to the first term, second term to second term. So, A sub k plus B sub k. What's the first term in the sequence A sub k plus B sub k? 3. Next term? 7. And the last term? 11. So now we have the sequence 3, 7, 11. That's this. Now, this says to add up those numbers. So what do you get if you do 3 plus 7 plus 11? 21. So I'm just going to write that down for a second. So that's what the left-hand side is saying to do. Now let's do it on the right. On the right, it says add everything in sequence A first. What's 1 plus 3 plus 5? 9. Now add everything in sequence B first. What's 2 plus 4 plus 6? 12. And what's 9 plus 12? 21. So it's just showing you that if you want to add 2 sequences together, you can do it either way. Why is that important? Because on the right, they're 2 separate summations. And on the left, you've combined it into one. That's the goal here, combining multiple summations into one. You can do exactly the same idea with subtraction. I'm not going to show you with numbers, but you could do it. So if you want to subtract 2 sequences, you can either subtract each number corresponding in the sequences, write those down, and then add them up. Or add up all the numbers in the first sequence, add up all the numbers in the second sequence, like 9 and 12, and then subtract those 2 numbers. Which way is more efficient? I don't know. If you don't like doing subtraction, then the second way is probably better because you don't have to do as much subtraction. Here, add up everything, you add up everything, and you do one subtraction. Here, you're going to subtract every single term, first term from first term, second term from second. So you have to do a lot of subtractions. Okay, and then the third thing. The third thing says that if you want to multiply a sequence by a constant, there's two ways you can do it. You can either distribute that constant to every term in the sequence and then add up the result, or add up all the numbers in the sequence first and then just multiply that answer by C. So let's show an example of this with numbers, because this is a little weird. Okay, somebody pick a number that I can use for a constant. Just don't pick 1, 3, or 5, because that might look confusing. 4. Okay. So what I want to find is 4a sub k. That literally means just take everything in a sub k and multiply by 4. So what would what's my first term?
4.
4, second term?
12.
And third term? 20. That is 4a sub k. Now this says to add everything here. What's 4 plus 12 plus 20? 36. Okay. So I just did an example of what's on the left. Now let's do the right. So the right, you do that first. Add up everything in a sub k. 1 plus 3 plus 5 gives me 9 times C is out in front. What number was C again? 4. What's 4 times 9? 36. Same thing I got doing it the other way. So when you want to multiply a sequence by a number, that's how you can do it. What's really the important thing to take away from this one? You're allowed to take numbers that you're multiplying by and move them to the front. So a number that you're multiplying by can always move to the front. And that simplifies the stuff that's here a little bit. Just take something away from it. Okay. So let's try an example using these two. Okay, so it says combine into a single sum. Notice when you combine things together, where it started and where it stopped has to be the same on each one. Okay. If this one started at 2 and ended at n, now we have a problem. You can't combine a sequence that starts at 1 with a sequence that starts at 2. You have to adjust something. They both have to start at 1. They both have to stop at n. Okay. And that's going to be our final answer. Wherever they start and stop originally, that's where they start and stop for the final answer. So sum k equals 1 to n. And this one kind of falls under our first rule. We're adding two separate things together. Think of this as a sub k. Think of this as b sub k. If you want, you can write them separate, like I have on the right here. Or just do a sub k plus b sub k. Put the two things that I circled in red, add those together inside the same sum. So you get 5k squared minus 4 plus 7 minus 2k plus k squared. And then it just becomes a matter of combining like terms. So if I combine all my like terms together, what would I get? So 6k squared, that looks good. Yep, minus 2k, that's good. Plus 3, yep. So if you had to do the problem above, it's a little bit simpler to just do this problem. Still a lot of work? Yeah, depends on how high n is. If n is in the millions, yeah, you're going to be here forever. All right. But at least we found a simpler way to write it. Any question on that? Now, in general, having this symbol, a summation, in a problem, we don't really like having that. Yeah, it's a convenient way to write something, but it doesn't give you a convenient way to actually do any math faster. So when we can get rid of these symbols, we want to. And that's what we're going to start to look at. So this is what I keep saying. A summation written in sigma notation is compact. It's very nice, very elegant way of writing something. But if you actually wanted to know what this was, you would still have to do this out. And what this is saying to do is add up the first 10 integers. It's a very simple formula. Formula is just k. Plug in 1 for k. 1. Okay? Plug in 2 for k. 2. Plug in 3 for k. 3. 4. I mean, even just writing this down takes a while. That's why I'm just going to put it dot, dot, dot. But that's a very common pattern. How do you add up all the numbers from 1 to something? Now, there's some tricks, and I don't know whether or not the story is true, but there's a story, if you look it up, that there was a math teacher and they were out one day and they left an assignment in class to add up all the numbers from 1 to 100. So most people, were sitting here, 1 plus 2, 2, 3, and then 3 plus the next one. And they're just trying to add up everything. But somebody else was kind of clever. And then what would we get? Let's do the last 4. 97, 99, 100. So 97, 98, 99, 100. Did anybody see a really easy way you could add up the numbers from 1 to 100? Remember, with addition, you can add in any order you want. So if you want to do 2 plus 6 and get that out of the way first, you can. But you got to add up everything eventually from 1 to 100. And the way I've written it, I'm kind of trying to give you a hint. Okay?
If you add the 1 to 99, you add the 2 to 99.
Okay. Yeah, that's basically, I'm just going to look at it like, if you add the 1 to 100, you get 101. And if you add 2 to 99, you get another 101. 3 to 98 is 101. So now it's just a question of, okay, how many 101s do you have? And how many would you have? 50. 101 times 50. There you go. You're done. So that's how you add up all the numbers from 1 to 100. But that's great. That trick works here. We're not always going to be able to find a trick like that for everything. So we're going to look at some special patterns. So I'm not going to go through this for every special pattern. I am going to go through it for the first one we look at. All right. In that summation that I just wrote, actually, you know what? Let's look at it as commas. Doesn't really matter, but. Okay. What do you get if you add up the first 1 terms in that sequence in red? 1. What if you add up the first 2 terms? 3. The first 3 terms? First 4 terms? 10? 5 terms. All right, I guess we're going to go a little beyond there. First 6 terms? And first 7? 28. Now, I'm going to show you a trick that shows you that this pattern is quadratic. Okay? That's a quadratic pattern. If you go like this, 1, 3, 6, 10, 15, 21, 28. Now find the differences between each one and the one next to it. What's the difference between 3 and 1? 2. 6 and 3?
4, 5,
7. Now we found the differences once. Let's find the differences one more time. 3 minus 2? 1. The number of times that you have to do that process before you get to a row that's all the same number tells you the highest exponent in the pattern. So I had to do it 1, 2. That's how I know this is a quadratic pattern. What is the quadratic pattern? Well, this doesn't really tell you that, but at least it does tell you it's quadratic, so you know you're looking for something with a square. Any question on that idea? This doesn't always work. This method of subtracting and getting a row that's a constant only works if your pattern is a polynomial. Try this with the Fibonacci numbers. You're going to be here all day. You can write out the Fibonacci numbers and find the differences. It never comes out to a row of constants, ever. So that means that the Fibonacci pattern is not a polynomial. It's not something squared, something cubed. It's something much harder than a polynomial. All right. Let's look at what I just wrote, and let's plug in some numbers and see what happens. Let's plug in 1. What's 1 plus 1? 2 times 1? 2. What's 2 divided by 2? 1. I just got the first number. Let's skip to the third one. What's 3 plus 1? 4 times 3? 12. What's 12 divided by 2? 6. I just got the sixth number, or S sub 3. If I did 5, 5 plus 1 is 6. 6 times 5 is 30. 30 divided by 2, there's my 15. So that is the pattern. It's a little complicated to figure that pattern out. The calculator can do it, but we're not really going to get into it. I'm just letting you know that if you went into Stat, Edit, and you typed in this table in L1 and L2, and then you went to calculate, you could calculate a regression. Now you have to know what regression to calculate. Well, I told you it's quadratic, so you at least know that. So you're looking for a quadratic, and if you tell the calculator, look for a quadratic pattern in the table I just typed in, the calculator will give you that. Okay. But we're going to go through a few formulas, and we're not going to type them in and figure them out on the calculator, because what the calculator would probably do is this. First, it would distribute out the n, and then it would write it like this. That's the same formula. I usually remember it this way. I don't remember it that way, but same thing. All right. So we're going to look at some formulas that are used to change something that has a sigma in it to something that doesn't. So that formula on this page right here allows you to get rid of this sigma because it describes the pattern that you're getting. Okay. Let's look at the first one. The sum from k equals 1 to n of a constant. So a constant is a number that doesn't change, like 5. Okay. Let's write down something like that. The sum from k equals 1 to 6 of 5. That's an example of number 1. If I plug 1 in for k in this formula, what do I get? Well, we're going to get a number. What's the problem? Why are people looking at this kind of weird? There is no k. All right. So there is no k. So try to plug 1 in for k and just write down whatever's left after you do that. What would be left? 5. That's all that's there. Now plug in 2 for k. Into what do you get? You get another 5. 3? Yeah. So no matter what you plug in for k, you're just going to keep getting 5s. How many 5s are you going to get? You're going to get 6 of them. So what's a short way of saying you have 5 6s? 30, how did you get 30? Multiply them. Your constant times n. So all you're doing here, this is the simplest kind of summation you can have. Repeated addition of the same number. We already have a very simple way to get rid of that. It's called multiplication. It's your constant times n. Now the difficulty starts to jump way up. This is the one we just looked at. Adding up the first n integers. That's the pattern. So like if you wanted to add up the first 30 integers, you could just say 31 times 30 divided by 2. That's it. Whatever 31 times 30 divided by 2 is, that's what the numbers 1 through 30 add up to. Now the patterns start to get even harder. So now you're adding up the first n perfect squares. 1 squared plus 2 squared plus 3 squared plus 4 squared. Things like that. So if you wanted to know what do the first 50 perfect squares add up to, you're adding up 1 squared through 50 squared. Every single number squared. All of them. Well, it's a little bit more complicated of a pattern, but not nearly as bad as trying to do that by hand. So if you want to know what the first 50 perfect squares add up to, all you got to do is plug in 50 for n. 101 times 51 times 50 divided by 6. And that'll tell me what they add up to. Big number? Yeah. So use a calculator. Why is it 6? We'd have to go through, we could use the calculator because this is a cubic, right? If you multiply, if you FOILed all this out, which I never do that, but if you FOIL it all out, you'd have n cubed something in the top and 6 in the bottom, and we could use the calculator to figure it out why. Figuring out that formula by hand, though, without a calculator, it's pretty hard. It's really hard to do. So that's not really something we're going to do. So it is just divide by 6. Okay, and this one, we're not really going to use this one much, if at all. But if you wanted to add up the first n perfect cubes, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way up to whatever you want to go to, that's the formula to do it. But we're not going to use that. So you can come up with formulas for anything. I mean, you can come up with formulas if you add up k to the 4th. I mean, there's tons of formulas. But the most common ones you guys are going to need are right there. 1, 2, 3. Okay. Any questions on those? Okay, so we'll actually try an example using, I'll show you how to use them. All right, so let's do this one, and we're going to skip that one. Okay, so I want to simplify that. So basically get rid of all those symbols. So when I'm done, if you said to me, okay, add up every number from 1 to 1,000 in this sequence, I don't want to have to write out every number. I don't want to have to write the first 1,000 numbers out and then add them up. I just want a formula that I can plug the number 1,000 in and I'm done. Okay. I don't have that yet. All right, so first thing we're going to do is kind of the reverse of what we did right here. Instead of combining this into one summation, I want to split it apart into as many as I can. As many, and they're going to get simpler each time. So, first way I'm going to split it is k equals 1 to n of negative 2k. And then I'm going to write another one. K equals 1 to n of 3. Now, look at this part. K equals 1 to n of 3. What's 3? We talked about that just a few minutes ago. It's a constant. K equals 1 to n of a constant. I've got a formula to get rid of that. It's just the constant times n, whatever your constant is. I'm not going to do it yet, but this one's good. I can get rid of that one. Now, let's go back here. Yes. Okay, I'll just drag that back where it goes. There we go. Now, this one, not quite. If we just had a k there, from k equals 1 to n of a k, I've got a formula for that. Right here. But I've got this negative 2 messing me up. But where can I put that negative 2? Yeah. I can move it in front. Right? That was one of the rules we looked at. So I can write negative 2 times the sum of k equals 1 to n of k plus k equals 1 to n of 3. Now that negative 2 is just going to hang out there. Nothing's going to happen to that. But there's something I can plug in for that. Let's look up what it is. K equals 1 to n of k. K equals 1 to n of k. N times n plus 1 over 2. And we're going to have to distribute that out. So I'll actually start by doing it as n squared plus n over 2. All right. Any questions why I plugged that in? Okay. And then plus, how about the sum from k equals 1 to n of 3? What is it?
Cn.
And what's our c in this case? 3. So plus 3n. Okay. So now we just got to combine like terms, simplify what we can, and we're good. 2 goes into 2 one time. So that's nice. So I'm left with negative 1 on the outside, n squared plus n plus 3n. You probably could have done this in the same step, but now distribute your negative 1. Negative n squared minus n plus 3n. And combine like terms. Negative n squared plus 2n. So now you've got a formula. So if you want to add up the first 20,000 terms in this summation, you don't even have to write out what the 20,000 terms are. Just plug the number 20,000 in for n, and you're done. And it'll automatically add up all the numbers, and you don't even know what they are. Any question on that idea? It's not too bad when you have something that's just a k. When you start to get into ones that are the k squared, it's kind of a pain to FOIL all that out. So these are probably the most important two you're going to see. Might see one in the homework like that, but on a test that would takes a little longer. So all right, that's that one. All right. So the last thing we're going to look at is how can we add up all of the numbers in a geometric sequence that has an n to it. Right, so remember, geometric sequence is when you multiply by the same number over and over. So 2, actually let's go like this. 3, 6, 12, 24. What am I multiplying by each time? 2. Now, what if I said to you, okay, I want you to take that sequence and add up the first 50 numbers in it. Well, you got the first 6. You got 44 to go. So if you had to write them all out, that's going to take a while. Right? And if you make a mistake on just one of them, the whole thing's messed up. So there's actually a formula to figure out, as long as your sequence is geometric, and you know the first term, and you know what you're multiplying by each time, you can automatically add up as many as you want. The first 50, the first 1,000, be the same amount of work. Okay? And there's your formula. So if you want to add up the first n terms, okay, find the nth partial sum, you need the first term times, as a fraction, 1 minus r to the n. Again, where r, we wrote that yesterday, r is called the common ratio. N is how many terms you're adding up. And that's your formula. So a sub 1 times 1 minus r to the n over 1 minus r. Where that formula comes from, that's actually not that hard to explain, but it's just not something I'm going to go through at the moment. I want to do the example. Okay, so here's a sequence. I've written out enough of the sequence. You should be able to kind of see what's going on there. I want to find the 12th partial sum. Does anybody see, what am I multiplying by? 1/3, right? So like the next term would be 2 what? 2/27ths. Right? You know what, let's do one that we can actually check easily. Let's find the 4th partial sum. If you want to do 12th, I mean, it's just as easy. But I've got the first 4. Let's add them up real quick and just see what we get. So we get 2 plus 2/3 plus 2/9 plus 2/27. Now, if that's all they asked me to do is find the 4th partial sum, I mean, I did that in 10 seconds. I'm done. Call it a day. If you wanted me to find the 500th partial sum, I'm not going to add up 500 numbers like I did here. It's going to take way too long. All right? But 4 is not that bad, and we can check it. So we get about 2.963. Just write that number off to the side. Now let's use our formula and see if we get the same thing. The 4th partial sum. What's my first term? 2 times, in parentheses, 1 minus, what am I multiplying by each time? 1/3. To the, how many terms am I adding up? 4. Divided by 1 minus r. What's 1 minus 1/3? 2/3. In theory, that should come out to 2.96. Let's see. I'm going to do this kind of one step at a time. So the numerator is 1 minus 1/3 to the 4th. So all I did was the top. I'm going to divide that number by 2/3. And now the last thing I'm going to do is double it. Times 2. And I get exactly the same thing. 2.962. So that gives you a nice quick formula to add up the terms in a geometric sequence. Can't be arithmetic. Has to be geometric. Okay. Any questions on that? All right. Okay, so homework tonight is 601. And it's 1 through 17.